And now, so good afternoon, everybody. It's a pleasure for us to have here Professor Hitzmann, Bernd Hitzmann. He's from the University of Hohenheim, Alemania, in Germany. And he is here and will share with us a part of his knowledge related to bioprocess analytics and control. And first, he will present us a little about the University of Hohenheim. After that, we'll go directly to the topic of our presentation. And then, thank you very much, Bernd Hitzmann, to be here. And it's a great pleasure to have you with us. And we have a strong collaboration with Bernd Hitzmann. And Mauricio belongs to this collaboration also. And we start this collaboration in 2001, 2000, and Mauricio and Luciani and we have the first together collaboration. And then thank you very much, Mauricio, for joining to this meeting. And then I am sure that you're not here to hear me, but Bernd, before I pass the words for Bernd, do you want to say something, Mauricio?
No, I just like to welcome Professor Bernd Hitzmann in our seminars. We are starting the seminars this year, and so I am very glad that we have here his presence today. As you said, in the past, Luciani spent some time working together with him, so it's very nice to be again in contact with his work. So thank you very much.
So then let's go.
Okay, thank you very much, Georgie, for the introduction. And hello, Maurizio. It's a pleasure for me to be here and have the opportunity to present some of my work. Before I start, I would like just to give you a short overview of the university I came from, that is the University of Hohenheim. The University of Hohenheim, you will see here the castle of Hohenheim, but here you can see Germany and where Hohenheim is. It's a part of the town Stuttgart, so it's a quarter of Stuttgart, and there is this, I would say, very nice university. I have here some numbers for Germany, just to know that we are a very, very small country compared to Brazil. I think it's really more a comparison to Rio Grande do Sul, because we have just 360,000 square kilometers. And we have roughly 80,000 million inhabitants. And as you can see here, this is the Hohenheim Palace, where the administration is in. And from time to time, I can go there also and ask for more money, but usually I won't get it. So the Stuttgart is the capital of Baden-Württemberg, which is one of the provinces in Germany. We have 3 faculties. That is, one is the agriculture science, then business, economics, and social science, as well as natural science. Sorry, I'm not used to the machine. Therefore, yeah, now here, so again, agricultural science, which is, I think, the most prestige one in Hohenheim, and I think it's also the biggest one. In fact, Hohenheim is the largest university in Germany if you just look at square meter. Otherwise, it's a very small one, as you will see. We just have less than 10,000 students. So business, economics, and social science is a faculty, as well as natural science. Then we have some focus points, that is bioeconomy, global natural security and ecosystem research, as well as health science. So I just have some numbers. I do not know, the numbers are very small, but also the persons are small. In total, we have 2,000 staff, and some of them are professors that are 130. Then also junior professors, 12. We have financial, I'll just skip it. It's not too much. It's although it is, I think, 180 million euro, and we get also some other monies as well as from research organization. Then to come to the students, we have numbers of degrees, that is 40, bachelor 12, masters 26. Bachelor program is just one, master also one for teachers, and doctorates are 3. In all over, we should have roughly 9,000 students, and we usually divide if we have how many women they are. And as you can see, in this case, the women are almost more than the overall men students. Then, I'll not do this one. As you can see here, this is the landscape of the university. And as I mentioned already, we are a huge university compared to the area. But this is not all of the area, but this is near close by where the castle is, which you can see hopefully here. And my department was here, which you can see. We have also some further area which is far away, where usually the farming is done. Then my institute is the Institute of Food Science and Biotechnology. We have there 10 different departments. One department belongs to the process analytics and serial science, where I come from. And as you can see, or maybe imagine here, we had also some snow, not too much in this case, but usually it's a lot. Then the focus points, I will not go in detail. As far as I know from Georgie, you can also get this video so you can look at the themes. And this is food mainly, but also biotechnology. And so we are investing molecular processes, then chemical processes, biotechnology processes, and physical processes. And these are the different departments which belongs to our institute. I just would like, if you have more questions regarding our university, just contact me. Otherwise, I just would like to go to the research point. And and this belongs to bioprocess analytics and control. One important thing is, if you can't measure it, you can't manage it, or you can't control it. So this has been said by maybe Peter Drucker or Robert Kaplan or David Norton. Both are more in the economic area, but I think this is also true for the area I'm working in. So this is also true for bioprocesses. You have to know something about your process, otherwise you cannot really control it. And I would like to speak about cultivation processes, bioprocesses, and the cultivation processes are really complicated because there are 3 phases. That is the cells, the microorganisms, and these are living cells. So sometimes they are in good mood, sometimes in bad mood. And this will, of course, influence the overall behavior of the process very much. Then you have the liquid medium phase, where also the substrate is in, where the cells get something to grow, as well as typically you arrate your process. Therefore, you have also a gas phase. And I will show you that you can get nice information also from the gas phase about the substrate concentration, or maybe the the product concentration. So a detailed monitoring of these three phases is necessary. And if you would like to understand what is really going on, you must measure there and get the information out of it. And only controlling the bioprocess automatically, I think you can really run the process well. Otherwise, it will be influenced typically by the human operator, and this is usually not a good thing. So what I will present you is first a little bit about measurements, different measurement methods, as well as also some detailed measurement which is done. Then I would like to focus on three different points. One is I would present you results from a gas sensor array, which is complemented by a Kalman filter to supervise a baker's yeast cultivation. And this is Saccharomyces cerevisiae. I will explain that further. Then I will present you fluorescence spectroscopy with a model-based calibration to supervise another yeast that is Hansenüller polymorpha cultivation. And at the end, something about Raman spectroscopy for CHO cells. These are Chinese hamster overall cells, culture monitoring. So these are animal cells. They are more complicated than yeast cells, and yeast cells are usually more complicated than bacterial cells. Then I will give you a summary, but I would like to show you also some further research projects we have worked on. So first, I would like to mention the difference in between online monitoring and offline monitoring. By online monitoring, there are typically three different ways. That is in situ measurement. So you put your sensor inside into the reactor, so there is a direct contact with the culture growth. Then you can also have an in situ measurement with sampling bypass. So you pass here the culture growth through, and therefore you measure in here still in situ. And then there is also an at-line measurement, which can be done by just taking out samples, and after measurement you just raise. But if you look at bioprocesses, usually online measurement is not done very often, so they are mostly use offline measurement, and that means you go to the reactor, you take a sample, go with the sample to the laboratory, and then you make your measurements, or you analyze the sample. And this, of course, is time consuming as well as money consuming. And you have for your process a huge time delay. So typically you cannot control your system if you get the measurement when the process almost finished. I just would like to show you that there are already lots of measurements done. There are physical variables, which you can see here, chemical variables, as well as biological variables. However, if you look in the industry, then they are not really used, because usually they are much too complicated. The industry, what they measure is roughly just the temperature, the pH value, maybe foam, if foam is a problem. Maybe they have also exhaust gas analyzers, but this is all. I think usually they do not really use a lot of measurements, although sometimes these processes are very expensive, especially if you look at pharmaceutical processes. That is the one I will show you at the end of my presentation. But if you look at, I would say, look at all these bioprocess variables, the most important, of course, is the biomass itself, and then the substrate. The substrate is necessary for the cells to grow, and therefore these are the most important, although the other ones are also important. pH value, I think you know from enzyme reaction, then the pH value is important, the temperature is important, but these are the only ones which are really used by the industry, temperature and pH. So there are also some other kind of sensors. These are called soft sensors. And soft sensors, they use just simple measurements, combine them by some software, and then get process information out of there. And the software which might be used uses differential equations to solve differential equations. I will show you one example of that. Then just regression models, maybe simple ones. Then neural network as well as combination of them, or maybe any other things where calculations are performed. Okay, now let's go to the first process I would like to present, and that is a gas sensor array complemented by a Kalman filter to supervise a baker's yeast cultivation. Although I say gas sensor array, this is a small array. It's just 3 sensors, but sensor array sounds much better than just sensors. The Kalman filter has been applied a lot. I just give you here an overview. If you are interested to see all these applications, then you can go to this paper, which is from 2021, so it's not too old. The Kalman filter already is used a lot, but mostly the extended Kalman filter is used. I will show you, and I think also with Georgi and Luciani, we had also some applications with the Kalman filter together, but we were now using not the extended, but a version of it I will discuss later. It's the unscented Kalman filter. So this is already published, and you can find this in the engineering in life science journal, and this is from 21. And it's about the unscented Kalman filter. Okay, I showed you sensor array. The sensor array you see over here, these are 3 different metal oxide sensors, and they behave differently dependent, for instance, on the carbohydrate. They are differently sensitive to carbohydrates. And these sensors we put in a small reactor, and we just used oxygen to get a good baseline out of the signal. And then we pump from the headspace of the reactor an amount of gas into this measurement chamber. And you can see here, this is a typical diagram of this kind of sensors. What you in fact measure is the resistance. And the resistance, the sensor itself, I do not know if you are if you know this kind of sensors, this metal oxide, they are very cheap. They are, I would say, less than 5 real. You get even maybe much less. And you heat them up a little bit, and then you can get nice results, as you can see over here, where you see a response when we put into the sample stream ethanol, on not ethanol as liquid, but just the gas above the liquid where ethanol is in. And what you can see here, these are the signals of the 3 sensors of our sensor array. And you see here that all 3 are really sensitive to ethanol. However, one can say that if you can combine all 3 signals, then of course you get a more reliable overall signal. Therefore, what we did is we used the principal component analysis of the signal and then related to the ethanol concentration. And how the overall system looks like, I show you. It's a complicated one. So I showed you this area. This is our sensor array with 3 sensors. And here is the oxygen, which is used to stabilize the overall signal. Some people are not using the oxygen. They directly just measure the resistance of the sensors. But sometimes when you have a drift, and a drift, of course, might be a problem. Therefore, we thought that it is much better to just use the oxygen to flush the sensor surface so that it is in a good situation. And here you see the bioreactor. We pump the headspace gas into our system. Just this is done every 5 minutes, just for 10 seconds. And I think I showed you the signal before. You will get a peak like this one, and then you can evaluate it. We used here the pre-processing also by calculating the peak height and area, and then we use principal component analysis to get the ethanol concentration out of it, and this is done every 5 minutes. So for supervising the process every 5 minutes might be a little bit too long. Therefore, we use an unsintered Kalman filter to predict how the ethanol evolved during the time, and therefore we used it for the filtering. Here is the filtering, and otherwise, if no measurement is present, then we do a prediction and make an estimation of the ethanol concentration, but also of the biomass, the glucose concentration, and furthermore, we predicted also 2 parameters, and these are the specific maximal growth rate on glucose and the specific maximal growth rate on ethanol. And then you are able to really know what is going on, because then you have the biomass, the ethanol, and the glucose, as well as the growth rate of the cells, which is a very important variable, which is dependent, of course, on the substrate concentration, but also on the pH, the temperature, the mood of the cells. So different things will influence. I do not know if you are familiar with the yeast fermentation. So usually it looks like this one. You have here the substrate. I can show it here, the substrate concentration, the glucose, which goes down. Here the cells, which are increasing. And as you can see, during the consumption of glucose, the cells produce ethanol. And when the glucose concentration is empty, then the ethanol concentration will be used as substrate, and the cells still are growing on the ethanol. It reminds me when I was young, when I had a plate, I just first took what I like best, and then afterwards the rest, and maybe the cells do the same thing. So if you would like to make a model out of it, of course, you can see the substrate goes down, the biomass is growing, and maybe you do not see it, but it's an exponential growth. And if you look at the equation, you have just the increase of the biomass is proportional to the specific growth rate and the biomass concentration itself. This is the growth rate on glucose, the growth rate on ethanol. So then you have the glucose concentration, it goes down, therefore you have a minus sign over here, and this is just a kind of, it's the yield factor which calculates how much biomass you will get out of the glucose concentration, out of the substrate. And the ethanol, there are 2 different phases. One phase is where ethanol is produced, so with the plus sign over here, and this describes this phase, and then a minus sign where the ethanol is consumed. Maybe you know the Monod model of growing, and this is similar to the Michaelis-Menten model, which you should know from enzyme kinetics. And you have the mu max, the glucose concentration Km plus the glucose concentration. The same we used for ethanol, but as you remember, the ethanol is just consumed when the glucose is empty. So in this phase, therefore, we add or we multiply in another factor to it. So this is 1 minus the growth rate on glucose divided by the maximum. And that meant usually if you know how the function looks like, if this is very small, then if the glucose concentration goes down, it then at the end, if it's less glucose, it will go down very fast. So most of the time, this and this is the same. So if you subtract it from 1, then it's almost 0. So that is why during this phase, it's always 0. And then here it starts very fast to get this part. Okay, then, oh no, this is hard. I should not use it. Then let's take a look to the Kalman filter. And I told you we use the unscented Kalman filter. The unscented Kalman filter is different to the extended Kalman filter, although the extended Kalman filter is produced for nonlinear systems, but you use for the calculation of all the variables, you use the first order Taylor simplification. So you in fact you linearize your process. And to not do the linearization, you can make the unscented transformation. And mainly this is by using special points which are transferred or transformed in the, I would say, almost right way. So, and with the points, you will get a rough idea how the distribution of the variables might look like. And this is much better for the implementation of a nonlinear system. In this paper, you will find on this internet page, there is a, from my point of view, a very good description of the unscented Kalman filter. And therefore, I will not discuss it furthermore. What we did is, because we do not know the real specific growth rates, we used the Kalman filter also to determine these parameters. And therefore, we just add to the state vector that the change of the max is equal to 0 as well as the one for ethanol. And we just use it for the prediction of these parameters. I will not discuss this. These are the parameters we are using. I think you can look afterwards. It does not make sense. But I would like to show you that we carried out 3 cultivations, that is BC1, 2, and 3. And you might see that the BC1, the glucose concentration is almost 9 grams per liter. Then here it's 5 grams per liter, and then almost 3 grams per liter. So the concentration of the substrate concentration goes down. And maybe I will show you root mean square errors, which are calculated like this. I think you are familiar with this thing, so I do not have to discuss it in detail, but we used also the sum of error in a percentage way, and I will show you this. First of all, the ethanol concentration, how it is measured or how it is predicted. You see here offline measurements, which are the squared. These are these points. Then you see the online estimated ethanol concentration, which are the round points. And then the line is the estimated. No, the points are the measured by our sensor array. And the line, the blue line, is the estimated concentration by the Kalman filter. And if you look at the values, I would say that except for the cultivation 2, where we have almost 10%, the percentage for the online measurement, just without the Kalman filter, I would say the values are not too bad. Usually 5%, I would say, always is a almost good measurement error. and in this case, only this one is larger. Here, for the estimated values from the Kalman filter, the errors are less than 5%. And I would say that the measurement as well as the estimation is well. These errors are calculated with respect to the offline data we obtained. And this is how one can validate it. It runs nicely. Here I have also the glucose values, the 9 gram per liter, 5 and almost 3 gram per liter, as well as the biomass, which is just estimated by the Kalman filter. And if you look also at these values, then in this case, just the BC1 has a large error of the biomass prediction. However, the other two are at 5%, and the glucose, I would say, very small values. I think this shows that the Kalman filter really is able to predict these variables well. I have also the prediction of the Mumex. Maybe I just skipped it because I see that the time is running fast, and Georgie told me I have just 1 hour. So we tried also just to give noise on the measurement and see how the Kalman filter works. And still, I would say it works quite well. I think these were 10% noise. These are the measurements which were given to the Kalman filter, and I would say that the prediction even still is fine. So I think that the gas sensor array is really able to measure the ethanol concentration. The proposed unscented Kalman filter just needs the ethanol measurement and then can predict the biomass, the glucose, as well as the growth rates. And I think this is very important information about the process itself. And therefore, it is really a big help for the control of such processes. Now, I would like to go to the next project that is about fluorescence spectroscopy, where we were using the model-based calibration. I think I already told you something about this, but I can show you now that we improve this thing. And I do not know how familiar you are with fluorescence spectroscopy. Here you can see the potential energy of a molecule. And here this is the electronic ground state, and here the electronic excited state. If I show how the fluorescence looks like, I usually put them away so one can see it much better. Although here, of course, this and this is the same. But if you then send light into your system, then you make an excitation of the molecule, and it goes from the ground state to the upper state. And what you see here also, these are the vibrational states of the molecule, because they can vibrate in very different ways. So it's, I would say, sometimes very complicated. And you see here also the rotational thing, because they can rotate, and this can take also up energy. However, if you excite the molecule, then usually you have this internal conversion. So it goes from, it starts usually from the ground vibrational state, although here it's now, I would say, not, oh, it's hot, but even at this temperature, usually all molecules will be in the vibrational ground state. So that's no thing. But the molecule, if it's excited, it will also go very fast to the vibrational ground state and then go back to the electronic ground state. And typically, this is then in another vibrational state. And as you can see here, there is lost some energy, as well as here is lost some energy. So the light which is sent out, that is this one, has much less energy compared to the one which has been sent in, and this is fluorescent. I think you are familiar, so I can go fast over it. I would like to present you something which is published in last year, and this is a collaboration with the group of Joachim Büchs. He is working at the university in Aachen, and they have developed a very nice measurement system. And we just got the signals, the spectra from him, and then we could calculate something, and I will show you what. And their system you can see over here. This is a microtiter plate, which is shaped here by this machine. So you have in here lots of several bioreactors. In fact, there are 42 small bioreactors. I show you afterwards. And of course, you get a lot of nice signals in one run. So you can make an inoculation very fast to all these little bioreactors. And he was measuring the fluorescence by a system like this one. Here you have a xenon lamp, and then you can select by a monochromator which wavelengths you will send in, and then you measure the emission of the molecule, and you can also have a monochromator over here. So you measure the intensity at different points. And the range is here from 280 to 690 excitation, and emission 310 to 720. Of course, the longer the wavelength is, then the smaller is the energy, as you know. Okay, a typical fluorescence spectrum of cells looks like this one. You have an area where the protein shows fluorescence. Mainly the fluorescence from tryptophan you can see, because tyrosine and phenylalanine, they have a smaller yield factor. They do not send out too much fluorescence light, but the tryptophan do it. Then you have here the vitamin and cofactor region, where especially NADPH is very important for cells, because you can see something about how they take up oxygen and how they use their substrate, as well as from the cofactors. So this is the information you get. The spectrum they send to us looks like this one. So you see here again that in the vitamin and cofactor region is something, as well as in the protein region. And of course, in the protein region, you have the signal of the biomass, because usually the biomass is produced, not mostly, but big part is out of protein. And here, this is a scheme of the microtiter plate. So there are little small holes in there, and the volume is 0.8 milliliters. So you do, in fact, really 42 cultivations in one row. And this, of course, is very interesting, because you get very nice signals during this during one run. In fact, they did 7 different cultivations with different initial glycerol concentration and different biomass concentration. And the question was, is it possible to use this information and then just get the information out of it without any further measurement? And that this happened, I think I showed you already in a more simple way. One thing would be how to evaluate the spectra is just take offline data corresponding online process spectra, and then perform principal component analysis and get a model of the spectrum. The other way around is to take offline data. So you go to the reactor, take samples, go to the laboratory, get measurements, then make a corresponding process model with it, then fit the model to the data, to the offline data, and get model parameters, then make some simulations of the process, and then you can use the spectra to get a model for the spectra. The advantage of this compared to this is that here you just can use the spectra which correspond to the offline data. And usually you do not take so many offline data, but you maybe take every minute a spectrum, but the offline data might be every 1 hour. So then if you use this is much better. However, it's even better if you use something like this one, and that will be the model-based calibration. And I would like to show you how this is done. In this case, the model is much more simple. You have just the glycerol and the biomass. You have here a delay time. So I show you just how the model looks like. It's very simple, mainly this one over here. Again, we have the growth rate and the biomass, but this factor, and the factor is just 1 if you have a lag, and if the time is larger than the lag time, and it's 0 if the time is smaller than the lag time. So usually the cells, they have to get used to their environment, and this takes time, and this is the lag time. And in this case, the Hansen-Nuller polymorpha yeast cells, they are somehow a little bit shy, I would say. They need some time to relax and then can grow. And this is really, as you might see soon, this is really a lag time which is several hours long. So now let's look at what one can do without any further offline measure. This is just the spectra, which you can see over here. Then the model, which can be simulated. If you know the initial concentration of glycerol and biomass, because you prepare the stuff. And you can just make a guess of the parameters. In this case, the mu, the growth rate, the yield factor, and the lag time. You maybe look at the literature, what they say, and you can use this. Then you can make a simulation, and you can use the spectra, just make the scaling of the spectra, make a principal component analysis, then split the data into a calibration and test set. With the calibration and the simulation, you prepare a model, regression model, and then you look the test set with this model is that it's the sum of error is that high or low. If it's high, then you just make an optimization algorithm. We use the particle swarm algorithm. Thank you. And then so we modified the specific growth rate, the yield, as well as the lag time, and do it as long as everything converts. And then afterwards, we will get the optimized process parameters as well as the model, the calibration, or the model to calculate the process variables out of the spectrum. And I would like to show you how this is done. We just used 3 principal components in this way, and then we calculated different errors. That is the error of the biomass, the error of the glycerol concentration. In this case, we changed a little bit the system. I will show you later why we use this equation. And then we sum them up. And this is then the model-based calibration if we minimize this way. However, we have also an optimized model-based calibration where we just use the biomass values. And I'll show you in the next transparency why this is done. And then when you know the yield factor, you can just calculate the glycerol concentration order. So, and this might be even better. For the optimization, we need some search space. I think I can just skip it because the time is still running fast. So here you can see the results we obtained with the model-based calibration. For this 7 different runs. 7. And what you see is that in overall, it looks already quite okay. So we have here the glycerol concentration, here the biomass, but always the glycerol concentration had at the end a deviation. And this was even higher. And I do not like to go back to the, but I would just show this one over here, that we use the first prediction minus the start glycerol concentration. That is because the glycerol doesn't show fluorescence. And therefore, the glycerol concentration is just very indirectly estimated out of the biomass concentration. And therefore, we think it is much better just to use the biomass and then calculate theoretically how the glycerol concentration looks like. And if you look at this one, this is the model-based calibration. And this one, as you can see here now, it's much better. This is the improved model-based calibration. So what one can say, I think I just go over this transparency. What I can show you that in all 10, the improved model-based calibration is better than the other one, although these are just the parameters which are compared to the process. They are almost, I would say, roughly the same, although here is a big difference, but I would say this is not so important. And if you look at the root mean square errors, you can see that for the improved model-based calibration, the values are always better than the ones for the other both. Although the classical and the model-based calibration is almost the same, as you can see over here. Although here we do not use any offline measurement, here, of course, the offline measurements are used, and therefore you can reduce the overall cost a lot by using this. And this is just to say that the improved model-based calibration really is much better. We use this kind of evaluation of spectra a lot. So here you can see that we start in 2003 with this kind of model-based calibration, and we applied it for different processes. And I think it's really worth to think if this might be a good thing. So I think I just skipped this.
But you can present. I think that we have time.
Yeah, maybe the thing is, this is about Raman spectroscopy, and maybe Raman spectroscopy is you have your vibration levels and you have the virtual level. And if you send light in, then you have the typical Rayleigh scattering. You send light in and the light comes out again. However, it can happen also that you send light in. However, the light which comes out has a longer wavelength, and this is the Raman scattering. Here you have again the vibrational ground state, and this is the first vibrational excited state. So, and this is the typical Raman signal you obtain. However, there's also another possibility, that is the Raman scattering anti-Stokes signal, and that is if you that your sample is in a vibrational first excited state, and you send the signal in, then you will get out more energy than you put in. And this is it's done. You have to heat up somehow your sample, otherwise it will not happen, because usually it will be always in the vibrational ground. But you can see it. So that is why I would like to show it to you. And here what I would like to mention is that the Raman signal typically is much lower compared to the signal which you send in. So the energy is 10 up to -6 lower. And this is really so you need a laser to get really such a signal, and we used 785 nanometers. And this is the typical way. The 785 you won't see. This is very dangerous. But if you will get it in your eye, the eye will be gone. That is a very big problem. So you have to really take care about the signal. In this case, we did offline measurement. I will explain soon. And here you can see the Raman spectrometer, where the laser, the monochromator, and photomultiplier is in this box. Here we did the measurement, and the signal typically looks like this one. In this case, we do not have samples from the CHO cells, but just wheat kernels. I would like to present you something which we have developed during the iConsensus project. We have been in there. If you are interested, you can go to the internet page. It's still valid, although the project itself stopped already. The internet page is www.iconsensus.eu. And we did a generic chemometric models for metabolite concentration during CHO cells by using a Raman spectrum. And as you might see over here, there are lots of people are involved, and especially the industry is in there. So, and this is the pharmaceutical industry. Here you see Bayer, then you see Sanofi, then you see Rentschler, and then you see JSK. This is GlaxoSmithKline. So these are really the very strong and powerful industry in Europe. And we were really very glad to in this project. Our part was we got the spectra from these companies and evaluated the spectrum. And the thing is that the companies, of course, they do not have the same spectrometer. So they have different one. We got altogether 1,700 spectra, and from different things. Two have the Kaiser system, but I'm not sure if the sensor tip is really the same. And then two others, they have the resolution spectra Raman spectrometer. So they are typically really different, and they do not collect the intensity at the same centimeter up at the same Kaiser. So, and that is what we got to produce the calibration. The validation data we did by ourselves. This is our spectrum, and we make a dilution series with glucose, lactate, glutamine, and glutamate. And this was done in a spectrometer obtained from Tech5 and InnoSpec, and with probe of in photonics, something like this one. So what we did is we used this huge amount of spectra of different spectrometers, of different process runs, of different bugs, of different reactors, of different media. Of course, they do not tell us how their media looks like. Of course, they do not tell us what the product is. They won't tell us almost nothing. They give us the spectra and said, okay, here you have the spectra, but they give us also offline data, but not more. And then we can just make the calculation. That is, we did this dilution series to get out, to test how our model looks like. And there is also in this project the Royal Institute of Technology in Stockholm. It's also from a university, and they were running this CHO cells for the IgG1 antibody production. And they got the cells from Genscher, as far as I remember. And they used, of course, also another spectrometer. So we have really different spectrometers, and then spectra from different cultivation runs. First, what we did is we make somehow normalization of all the spectrometer. We did a cubic spline interpolation so that we got always at the same wave number the intensity values. And then we just took a range in between 300 and 3,300 Kelvin. And then we make a pre-processing after that. That is, we calculate the first derivative, and then we make a standard normal variate normalization. I think I just skip it because the time is running. I just show you how just ordinary spectra should. They said to us, the companies, we should not say where this spectra comes from, but there are so many, so they said, okay, it's no problem. And if you make then the pre-processing, that is the first derivative, and then the SNV transformation, the spectra, all spectra look like this one over here. And then we just look, if we would, from these 4 companies, if we would just make an external validation, I just will skip this one, would make an external validation, then you see that the error is really huge for glucose, and the R squared is also very low. So this is not, it's not possible. If just you take measurements from one side and process them, just one side, the other side, these are 3-4 different processing things. But when you look at the calibration, if you take all of them, then I would say they look not too bad, 0.96, 0.96, 0.98, 0.93. And this is the normalized. As you can see, it's just normalized. They don't want that you see how, in which range they were measured, the stuff. We know it, but if we would say it, then we have to pay a lot of money. So I'm sorry for that. And if you can see here, this is also a prediction. So we split the data set, and then I think it looks really quite nice, although there are really different process runs. And then we did our dilution series. And as you can see here, that the highest value, it's a big error, but down here, it's really good, although it's just a special medium, and then with the different glucose, lactate, glutamine, and glutamate concentration. The worst results are obtained by the glutamate. The other ones, I would say, are quite okay. Then the data from the Royal Institute of Technology, I always think Royal Institute of Technology sounds great. And unfortunately, yeah, it's okay. What you can see here are the glucose concentration, and it looks strange somehow. We do not know if the Royal Institute has measured really fine. I'm not sure why this deviation is, but what you can see is the overall evolution is the same. And here also, this belongs to this one. This one, it fits. I do not know why. Here, the deviation, this fits also almost. It's unclear why this is the case. Although you see roughly that maybe there is information in. And if you look at this one, it's a very narrow concentration range. If you look at this one, it's also the glucose. This is from 0 to 100, although this is not a good thing, but even to 40. So from 0 to 40, it's quite okay. Why then this happens here, I do not know. But the lactate concentration, if you look at the lactate, it's fine. So therefore, I would say Raman spectroscopy, I think this is also for all spectroscopy. Calibration is thoughtful, so you have to do a lot, although maybe a recalibration is necessary, although I would say if you use the model-based thing, then it might be not as problematic. It's non-invasive, it's no reagent are necessary, no contamination risk because you use light. It's a fast situation. Many analytes can be determined in parallel. That was the glucose concentration, lactate, glutamine concentration. Improves the automation grade a lot if you use it. Becomes more and more affordable because in former times a Raman spectrometer was very expensive, always attentive, never busy or tired. So I just would summarize that the gas sensor array, 3 sensors, was working fine. The improved model-based calibration did a good job. The fluorescent spectroscopy, I think it's very nice, and you can predict also stuff which shows no fluorescence. You can calculate it somehow, but the Raman spectrometer, I would say, from the point of spectrometer, you will get the best information because you really get signals from all these compounds in one spectrum. And I just would maybe mention our further research projects, what we have done. I told you that I come from a food institute. Although one thing I like very much is experimental design based on Fisher information. That is one thing I like very much. We did analysis with wheat flour. Then we have analyzed the cleaning process by modeling and supervision. We have the dough fermentation, also modeling, image analysis, closed loop control by using fuzzy knowledge and compared it to PID control. We used gas hydrates as leavening agent. This is one of the last projects I had. We have, for bread making, we used image analysis just to see when the bread should be harvested. Then the bread production as well as the recipes, we make an optimization for this. Bread production, usually a company has to decide what they have to produce first and what last, and they have usually different products, and I think it's worthwhile to make an optimization. Then we have analyzed milk, and we could analyze if there are some strange stuff in the milk. And also, I think milk foam is important for barista stuff. So we could make a model to say this milk is good for barista, this is not as good, although the model, I would say the error is a little bit higher than we were hoping to get. Then analysis of copy, this is still running, and there we were looking for adulteration, and we investigated the roasting process and looked if we can optimize this. Then shea oil adulteration. Georgie told me about shea, and he gave me a yogurt and said, "Oh, put shea in there, and you will see what happened." And I was very much astonished. And therefore, then we had also this project, wheat analysis with Raman spectroscopy, biogas process analysis. So really different projects we were running. And I'm running out of time, but I would like to make some suggestions to students. Measure whatever possible online. I think this is for processes, this is really important. Then use any piece of information online. If you have a model, then try put the model in the computer, let it run, and see during the process and see if you can get more out of it. Train your math ability. I think this is really important, that you are not astonished if you have to calculate the Jacobi matrix or something like that. Although if you use the unscented Kalman filter, you do not need to calculate the Jacobi as well as the Hesse matrix. It's not necessary. But I think this is important. Be open-minded for new things. I think this is clear. I must not say. Do not give up if things went wrong. I was so many times disappointed, but I think at the end, really, just go ahead, try again. I think then you really will survive. do networking. This is also very important. And if you are at the conference, then just speak with people. Just ask them questions, even if you know already the answer. It's just to speak with them, and then maybe you talk more with them, and I think this is important. Be always attentive, never busy or tired. I would like to give you just a small example, which I really like a lot. You know Mr. Gauss, the least square algorithm, and he make one paper. Unfortunately, it's in German, but he wrote here the induction law. This is about magnetism, and if you have a wire, then you can measure electron. And he wrote, this is the translation, found 1835, January 23rd, in the morning, 8 o'clock, before getting up. So he was laying still in bed and he was thinking about the stuff. Therefore, I think this is really worthwhile. Do not, you are always should think about your process, and maybe you will get nice ideas as the one Gauss had. So I would like to thank, of course, all the co-authors, especially Olivier Paquet-Durand, Maya Ruhl Islam Bayes Barbour, Rahim, then Christopher Berg and Jochen Wix from the Aachen University, of course, the ones where we get the money from. And I would like to thank especially Luciani and Georgie. I think it was really a very long and very worthwhile collaboration. And I'm looking forward that maybe we can still have more collaboration and discuss more about the stuff. And I would like also to thank you for your attention. Thank you very much.
Thank you very much for your presentation. And now I have one time I brought my mate tea with the dogs. He was there, and then I said,
yeah.
Yeah.
Göttingen is near Hanover. It's a little bit south from Hanover. And in fact, Gauss was born in Brunswick, so which is also near to Hanover. And I like Gauss, the stuff he did. It's really amazing, and he did very good stuff. Maybe now I still have some time, so I can. The thing is, Gauss, you know that when he published the stuff about the least square algorithm, he didn't mention that he used the square algorithm. The thing was that Mr. Piazzo, that is an Italian astronomer, he was looking at Ceres, which is a planetoid, and he saw out that there is a planetoid, and he wrote where he found it. And he had many measurement points, but then he felt ill, and then maybe the weather was in the way that he couldn't find it, and then he couldn't find it anymore. But he published the measurement points, and Gauss used the measurement points and predicted where the planetoid can be seen. And that he published, and then he just became famous, and that was in 1800. And then after a while, somebody else published the method of least square. And then Gauss said, oh, I used it 10 years before. And he published it also. And there was this little small discussion, but everyone knows if Gauss said he had used it, then of course nobody will don't trust him. So although somebody else published this method before Gauss, the first one who used it was Gauss. And I think it's a nice thing that you should think about, even if you do stuff which you think is not so important, that you do not publish it. It might be very important to publish it. So, and then you might become as famous as Mr. Gauss.
So we can open for discussions and questions. I don't know if our colleagues have one question, then we can give you the opportunity to answer, to ask this question. Then Mauricio, please.
Okay, Jorge, thank you very much. I would like to thank Professor Hitzman again for the excellent presentation. It was very illustrative and very interesting. All the cases that you presented were, you see, made us think about a lot of possible applications, other applications. I'd like to ask you to comment a bit about the problem of control. For example, your presentation sometimes it seemed that the objective was more like supervision than process control. If you were to apply process control, what would be the challenges? I mean, like a closed loop or developing a model for an MPC, and maybe if you had the need to update the model, would it be very difficult to do, you see, the calibrations that you presented for an industrial process, you see, online? I would like to ask you to talk a little bit from this perspective for control application.
Okay, thank you very much. Yeah, with control, I think you mean closed loop control. I would say in Germany, we speak also about control if you do not have the closed loop control. In closed loop control, I think if you remind the data from the Raman spectrometer, you could use it without any problem, because there, I think that you really, that with the Raman spectrometer, it's a direct measurement, not an indirect measurement. However, the data are presented from the ethanol concentration or the glucose concentration, from the yeast fermentation, and from the Hansenüller polymorpha fermentation. Then this is indirect measurement. And I think this values you cannot really use for closed loop control, the ethanol concentration. It might be possible that you can use it with the gas sensors, but not with the fluorescence measurement or the fluorescence prediction of the ethanol concentration or the glucose concentration. Both do not show the real fluorescence signal. The concentration is more calculated indirectly by using the biomass. You see the biomass increasing, and therefore the substrate concentration must decrease. And if you use then this glucose concentration for closed loop control, then I'm almost sure it will not work fine. So it depends on what kind of signal you have. I think we used also the fluorescence data for closed loop control, but this was more a heuristic control process because we there were using the NADH concentration. The NADH intracellular concentration, which is obtained by fluorescence, will go down. I think now I'm confused, or maybe go up if the substrate concentration is consumed. And therefore, you can see when the substrate concentration is consumed, and then you can act and maybe increase your feed rate so that the NADH fluorescence will go into the old position. And this is possible, but not by using the variables I presented to you. Maybe it can be possible by the biomass concentration, but not by the other variables. I hope I could somehow answer.
No, that's well. Yes, I think there are other people. Thank you for the answer, and I will pass for the others. Okay, thank you, Professor.
So
Thank you.
thank you very much for the question, Mauricio. We can then further continue this discussion. Argemiro, do you have any question? Yes.
Yes, thanks, George, and thanks, Hitzman, for the presentation. I don't know if you remember me, but I was in Porto Alegre when you was first visiting George and Luciano.
I remember.
Okay, but now I'm real since.
I remember the name, but I do not know your face right now.
Okay.
Ah,
Okay, maybe you can.
hello.
I'm here. Hi. Yes. Well, I have two questions for you. One is regarding to the gas sensor array. You have shown an example for the yeast fermentation for an anaerobic process. When you have an aerobic process with a lot of gas comes in, do you have some experience on this gas sensor array? Do you be sensible to measure, for example, ethanol concentration in the gas phase? Have you some experience on the aerobic fermentation?
It's related to aerobic fermentation. You mentioned that you're using oxygen for baseline.
Yeah.
And then you took from the fermenter the gas phase to measure the ethanol concentration.
Yeah.
And Argemiro is asking about in the bioreactor where you have aerobic fermentation, not anaerobic fermentation, or aerobic bioreactor, how it will be.
I think it will be almost the same. Maybe it might be even easier if it's an anaerobic fermentation, because then, of course, you will flush your sensor system with oxygen again. But this will not happen inside of the reactor. Our sensor system was outside. It was ex situ measurement. In fact, I know that this sensor is also used for the ethanol concentration in beverages, and there, of course, is also no rated process. It's just that the ethanol will be in a stable system, that the ethanol in the liquid and the ethanol in the gas phase above the liquid should be related to each other. Then I think it should be possible. And I think it's also for anaerobic process possible. The big advantage, maybe I can mention again, is that these sensors are so cheap. We used 3 sensors, and maybe because it was working already, we didn't use more. But it's easy to do, and you can get these sensors, also very different sensors. I think now also Bosch has. We thought to buy this Bosch sensor. It's also not so expensive, but there you can choose also the temperature, and therefore you can also have temperature gradients, and therefore you might get much better sensitivity for your signal you need if you just play a little bit with the temperature there.
Okay, and this comes to my second question regarding what you mentioned in the last, this is just shifter sensors. But in regard to the Raman and the fluorescence spectroscopy, these are, despite the calibration effort, they are very expensive devices. And how I think this will be applied for in the real industries, to put this online, to have all these expensive sensors, the Raman, of course.
Maybe I can mention, we have also another project where we just were using our expensive fluorescence sensor to see what are the main important excitation emission wavelength. And then we designed a new sensor system out of LEDs and
And filters.
LED, you need LEDs, filters, and also something behind the filter. I do not know the name yet. It's a sensor where you can just measure the intensity of the light which comes, and these are also cheap stuff. So we build a system out of, I think, 3 LEDs and 3, I do not remember the name yet, and also I think how many, and several filters. The most expensive stuff was the filter. However, in overall, as far as I remember, the hardware cost was less than 500 euro. So you can build a very small system out of this LED, and I do not remember the other name.
The detector of the light.
The light detectors, yeah, they are. It's a system where the resistance is changing due to the light intensity. Photo multi, no, not for multiply. Photodiodes. Yes, no, thank you very much. Photodiode and LED, they are really not very much expensive. And in fact, I know that now we were using this BioView system, which was built by a company from Denmark. Now this Denmark group, I think they are thinking about building a system out of LEDs and photodiodes and filters, and this will be much cheaper compared to the 40,000 euro you have to spend for the fluorescence sensor. The Raman spectrometer, they are not as expensive as maybe 10 years before. I think we spend around 15,000 euro for the Raman spectrometer. So it's of course it's still a lot of money. However, you might improve your process a lot if you get this information.
Sure. Yeah.
And
okay, thank you very much.
And we have also in the past a collaboration where we do this customized sensors. Then one of our research here is to develop these customized sensors. And now in the future, close future, we will have the Julio. Julio will work especially for developing customized sensors based on spectroscopy and Raman spectroscopy. But the idea is that to use a standard system to select the excited and emission layer, and then to a specialized sensor, customized one that is cheaper to be applied and easy to maintain in a real.
I think you can make really a business out of it. If you have a good spectrometer, then you can just look what are the main important excitation and emission wavelengths and can build a very cheap one. I think as the hardware, I usually should have also a presentation about this system we developed that was for sourdough fermentation. And it was really a very, from my point of view,
and Cassiano has worked with.
Yeah, I think he worked.
Lucas also.
They were using the ant colony algorithm for checking what are the best wavelength combinations.
All right, let us have additional question from our audience here. Cesar Augusto, please.
Hi, can you hear me?
Yeah.
Yes.
Thank you very much for the presentation, very interesting. My question is, how do we include metabolic production variables in the control monitoring phases? I mean, how to predict metabolic production rate based on few measurements, using, for example, hybrid models of metabolic fluxes?
I think you can, there are also models around where also metabolic compounds are included in. Although maybe you know the models which are presented by Professor Royce. He used models with, I think, 1,000 parameters or even more. I'm not sure if this is really possible, but I think maybe you can somehow simplify this really huge models where only the important steps are included in, and then maybe you can really determine the parameters of these models and can use it by making measurements like I presented. And maybe even if you cannot measure some compounds, maybe you can use this approach with a model-based calibration. You can see if your model might fit to the measurements which you did, and then you can somehow get the parameters out of it.
Okay, thank you.
So then now we change to our people here in the 3D version. And then anyone has any question? Pardon, do you have any question?
Yeah, I have one, but it's in the sensor array, how can you select, how did you select the 3 sensors, and how can I select the sensors?
We just take the sensors, make measurements, and see if they show any response. If you present the sample to them, if they do not show a response, then you can kick them out. Although I think it would not be a big thing if you still let them in and just gave do not consider the signal, because they are not expensive. The thing is, I think that the graduate student who were using or were building this system, he had a measurement chamber, and due to the volume of the measurement chamber, he could not put more sensors in there. That is the only reason. But and he could show that it was working fine. Therefore, even if it's just 3 sensors, we call it array. Although you can just put more in there and make a sound better if you say, oh, there are 10 sensors. Even if 7 sensors do not give a real response.
Thank you, but because there is lots of these sensors. If you see MT1, 2, 3, and I think there is more than 20 or 30.
Yeah, the thing is that they are, the stability of the sensors might be the problem. It depends on they improved a lot during the last years. This kind of sensors are around, I would say, several years already, metal oxide sensors. However, they improved a lot, and as I told you, this sensor from Bosch, you can change the temperature, you can have temperature gradients on there, and therefore you might much better get the signal out which is necessary.
Thank you very much.
So this, okay, thank you very much for the presentation. I have a question also regarding the gas sensor array, and it was somewhat similar to Professor Ejim's question. But you mentioned that it's an ex situ process, and
furthermore, you predict the concentration in the liquid by measuring the concentration in the gas. But it works.
Would it be somewhat advantageous, or would it matter if you could like recycle the gas and put it back into the reactor if it was maybe an aerobic fermentation or something like that, to maybe not have to dispose of the gas phase or something like that?
You know, but usually you, due to the fact that you array, then of course you have you produce more gas and more. So it would be easy. The thing is, if there might be worthwhile compounds in the gas, of course, I think it might be interesting to somehow wash the gas or try to get the important compound out of the gas. I think that will be possible.
And this is it. My second question we already answered during the presentation, so thank you very much.
You're welcome.
Have you applied this gas sensor to other components? You showed here for ethanol, but have you used it for other things?
We don't use it, or we haven't. We were using it also for during the corona phase. We have used it to measure the carbon dioxide concentration, and if in a room the carbon dioxide concentration were too high, then we know we have to open the window. Unfortunately, it was during the winter, so we didn't like to open the window too much. But it was a cheap and easy system to say now it's the time to open the window. So carbon dioxide, it's easy to measure, and there are also the special sensors. They say this is very sensitive to carbon dioxide, but you can use it also for other volatile signals, and they are used, but I do not know really which compound already has been used by these sensors. But they are coming up more and more.
Okay, thank you.
Deborah, do you have any questions? I
So
have
that's been a question.
Are we still online?
Yeah.
yes, so, but we have already several questions. But I would stop them if anyone have any additional questions. I can stop right now, and then we can continue the discussion on this topic because I particularly interest on it, and then we can discuss in detail with the students. And if no one has any additional questions, so that we have already passed 3 o'clock p.m. I think that it's time to finish our presentation. And if anyone have any other question, please tell us. If not, from my side, we can finish. And the last word I will leave for our master of seminars, Mauricio, please.
Yes. Thank you. I'd like to just announce the next seminar. It will be in March the 25th, and it will be given by Vipu Man. He has concluded his PhD at Columbia University. He was supervised by Professor Venkata Subramanian. So he works with artificial intelligence, and he is presently working at Bristol Myers Squibb, a large pharmaceutical company. And his presentation will be about the use of large language models to the design of pharmaceuticals. So I'd like to invite everyone now, and then I will later give more details about this presentation. And thank you very much again, Professor Hitzman, and thank you, George.
We thank you for you being with us here, and it was a great pleasure. And we have started this year quite well. The presentation of Professor Hitzman was wonderful, and I think that this year we will have several very good presentations. I see you next time then. Bye bye.
See you, Mauritius. Bye bye.